Alright, in this video we're going to finish up operator overloading by talking about the post-increment, pre-increment, post-decrement, and pre-decrement. So what do I mean by all of those? In the use of C integers, I can do something like, this. Or I can do something like this. Additionally, I can do this with the minus sign. And this will either increment or decrement the value of the variable. But things get a little bit complex here because Q is just not some integer. It's a class that has attributes, 3 attributes specifically. So how can I go about implementing this post and pre-increment and post and pre-decrement for a class like this? Similar to how we've done for all the other operators before, we need to overload this operator. So here I have the pre-increment and the pre-decrement code for overloading the operator for a class. How I want to go about either the pre-increment or the pre-decrement, I want to either increment all attributes of the class or I want to decrement all attributes of the class by 1. So the way I do that here is that here I have my set x, set y, and set z, my setters, and when I want to do the pre-increment, I increase them by 1 and then I return the class itself, which is pretty simple, right? I just increment every single attribute in my class. And let's say, for example, if it included a string, I would probably just increment all the numerical data in the class as the pre-increment operator. However, you have the choice to increment how you want to, what you choose to increment or what you don't choose. If you wanted to, you can just increment x or y or z, or you can do x and y, or y and z, or x and z. It's up to you and you have total control over it. But for myself, I want to increment every single attribute. And for the pre-decrement operator, I'm going to do the same thing. I'm going to set all the attributes to 1 less than itself. Right? So x will be x minus 1, y will be y minus 1, and z will be z minus 1. Just a normal decrementing. So if we go down to our main here, you'll see, and I commented all this out so that way it's not so bothersome. So you have the pre-increment and the pre-decrement. So why don't we go about printing Q? Now that we have our print statements, why don't we see how the program runs? We have it here, 2 to 2, right, because we did an increment, so I went from 1, 1, 1 to 2, 2, 2. Then we have our pre-decrement, which will bring it down to 1, 1, 1. So we know that the syntax works. We need to check if it works with the other scenario that it is used for. What do I mean? Well, pre-increment means that we do an increment and then we do some sort of action. So if I say, for example, right, so what this is essentially doing in terms of expanding what's going on, I'm doing b plus equals 1, or the equivalent, right? When I do p plus equals 1 here, I'm incrementing every single every single attribute in the class, and then I do point 3d z equals t minus b. Right, that's what this translation means. So if q is 1, 1, 1, we're going to be subtracting 2 from each one of these values, so we should have 6.3, 5.6, and I think negative 1.8. I don't know. We'll figure that out. Anyways, why don't we run this code and see that this works? I gotta stop calling my p variable q. Here's our new point, and this works correctly. We have 6.3, 5.6, and what I think would have been a negative number now is 0 because we don't let our 0.3d be less than 0. So why don't we look at a pre-decrement? And if we do a pre-decrement, since the original values of q are 1, 1, 1, if we do a pre-decrement, that should be 0, 0, 0. Meaning that z will be essentially unaffected. There will be no change in its values. It'll be exactly equal to t. So why don't we show that? And look, yes, it is true. So our pre-increment and our pre-decrement work. So now we have this. So here's the pre's. Pre plus plus. And this will be minus minus. So why don't I work on the post increment and the post decrement? And here we have it. So what makes the post increment and the pre-increment different is that the pre-increment is going to have no arguments and the post increment is going to have an argument. For my sake, I have an integer, and you'll notice that I do nothing with it, and that's okay. However, this is the way to denote that this is going to be a post increment. And I do the same thing with the post decrement. It's very similar to the pre-decrement. However, post decrement has an argument. Again, it's never used, but that's what lets us differentiate the post increment from the pre-increment, as well as the post decrement from the pre-decrement. So let's kind of look at the body of the code for both of these. They're largely the same, and I actually abuse the fact that I have the pre-decrement and the pre-increment already declared, so I use them. So the idea is that I have this, and I set it equal to, a copy, a temporary point3D that's going to have the current attributes of this data, and then we increment ourselves, but we return the copy. So this allows us to do since this is post incrementing, this allows us to do the action first because we're returning the copy first, but right after the action is completed, we have an incremented class. Same thing here. I make a copy of the current instance of the class, and then the class itself is decremented, but we return the copy, again giving the illusion that we do our action first and then we decrement. And again, I mean, we're being a little abusive here or exploitative of the fact that we already have declared our pre-decrement and our pre-increment, right? So here I have the pre-increment for the class, because when I do this, when I call this, it's a point3D class. So if I do the pre-increment for the point3D class, we already have it defined above right here. And same thing here, when I do the pre-decrement for this is a point3D class, and well, wouldn't you know, we have the details on how to do that right here. And this is kind of similar and using the same concept as overloading the double equals operator and the not equals operator, right? Once you have one of them defined, you can use it to define the other, and we're using the same thing here. So why don't we go down to main, and well, here we have this code where we test the pre-increment and the decrement. Now, why don't we test the post-increment and the post-decrement? Here's what my tests are going to look like. Now we have Q that's set to 1, 1, 1. We're going to print that it says, okay, 1, 1, 1. Then we're going to add 1, 1, 1 with T, right, 8.3, 7.6, and 1.2. The results Z doesn't really matter. I mean, I guess we can print that too. So the idea here is that I have, we're gonna use Q and then we're gonna increment it. So since Q is 1, 1, 1, when we add it with T, Z should print out 9.3, 8.6, 2.2. No goodness, when we have Z here, well, we're gonna have 2 divided by these numbers, which will give us something. I don't know what it'll be, but it'll give us something. But then Q will decrement. And actually the result of the third element should be close to 1 because it'll be 2 over 2.2, which would be really close to 1, but still less than 1. So we'll watch out for that. However, Q will be decremented, and instead of being 2, 2, 2, it'll be 1, 1, 1. So now why don't we see the execution of this program? And here we have it. So the result is just as I expected. We have 1, 1, 1. We add 1 with 8.3, 9.3, 1 with 7.6, we get 8.6, 1 with 9.2, 2.2. And then Q going from 1, 1, 1 is now 2, 2, 2. So then we do the division of 2, 2, 2 over this number, and we have numbers less than 1, but one thing that makes me confident that this is 222 divided by these numbers is that this number is really close to 1, because we're going to have, when we have 2 over 2.2, that's really close to 1. So it makes sense that this is 0.9, because if this was 1, right, 1 over 2.2 would be really close to 1/2, meaning 0.5. So I have confidence that since this result is really close to 1, that we're doing the division of 222 divided by 9.3, 8.6, 2.2. And then lastly, we print the decremented result of Q, which is 111. And here our tests are complete. It's good. It looks like our operator overloading is functioning correctly. One last thing that I want to say is that overloading operators is not always needed. It's a case-by-case scenario. Something to think about is that, well, with point 3D, you know, if we have 3 points in a three-dimensional space, it can make sense to do arithmetic on them. You know, if you need to add 2 points, subtract 2 points, scale them to something, I mean, doing these mathematical operations for a 3D point kind of makes sense. However, for something like, you know, a vector, I created the vector class earlier before, that kind of doesn't make sense to need something like, you know, a plus or a minus operator. I mean, those can be involved. I mean, you can treat those kind of like matrices and do arithmetic with that, but that's a case-by-case basis, right? You know, you might create a vector class that is used for matrix analysis or linear algebra, and there it will make sense to kind of do these arithmetic operators as well as the equals and not equals operators. But sometimes if you just need to have a vector of strings and stuff, you know, you may not need a multiply operator, because what are you going to do if you multiply like a vector of strings, right? So overloading operators, just because you can overload the operator for the class, doesn't mean that you should. But anyways, that about wraps it up for operating overloading, and I'll see you in the next video.